Okay. So, oh, this all works for, does this work for Max? Oh, so I got it on the PC.
Oh, okay.
Does this have a laser? Okay. Laser and just a click, because I can just, I practiced yesterday without it. It was.
Yeah, right.
The next couple months on that.
How much time we got, sir?
5 minutes, it looks like.
5 minutes? For you, Tim?
Joe, you want to try? One Mark's there in digital land, and Robert, my sister.
Sorry, Ryan, this is just a flashlight.
Oh.
Which is give you a thing.
Okay, so 2.
Who else is on this? Mark, JD's on
Actually, just go to Facebook. Just go to my page.
I really think he was
Kitties and everything.
Thanksgiving with your mother? Was your partner?
No, she lost both her parents. But her brother and sister-in-law.
They live in the area.
Oh, wait, yes.
I clicked this other thing, it said live event will begin in 2 minutes.
And she works at.
Okay. Huh.
You have to go down every day.
Oh, yeah, good job. Thanks for doing that. Yeah, I think it's.
Oh, thank you.
And I know, like,
She's awesome.
She teaches 4 classes. So, do you have like 2 sections or anything, or is it more different?
But yeah, she did 2 sections. So that course.
When is that?
It's
Still a lot of
grading.
Yeah, grading. Yeah, grading.
She has papers. Essays. All right, congratulations on your review. Yes.
Oh, thanks. Yeah. No, I think that's kind of what I expected as far as kind of the quick go.
Brought up the same things I would have probably kept.
Right.
Hammering away.
Yeah. Yeah.
So to have a review the back there quickly.
Oh, thanks. Yeah. Yeah. No, I think that's kind of what I expected. Okay, I think we're live streaming out to the world.
So, I have a lot of trouble getting track. I'm not sure if she's bad.
I'm gonna mute these notifications.
I used to like study like safety.
Right now, is dissertation review too, is that the final?
As of now, yeah.
You know, I forget it. I'm not
Good. I don't know. It doesn't. I mean, I think I could maybe figure it out, but.
Well, yeah, and then you would have.
Yeah, we do a quick introduction.
Yeah. I was doing a clean out and I unpressed it.
Thanks for fine, though. I didn't miss it yet.
Yeah.
I wouldn't miss it eventually. Okay. So. how to do it.
Sure. That was a natural resource. Yeah, one interview, one back.
Actually, and the one that's going interview is actually.
How are you?
Yeah, I was checking Conceptual Model now. It's the Ecological Society.
Yeah. So, REM, the other paper.
Yeah.
Oh, thank God.
The wrong people say.
And I'll check on
Yeah.
the 2 lights off.
Yeah, I think that's pretty much the full house. You can start
Okay, yeah, no, I'm ready. Or we could just signal something.
Yeah.
I just, when I practiced it, it was clear. I just checked the lights.
I'm not gonna do it externally right now. So, we're actually just like a couple weeks on now. Oh, right on the edge of like, not wise.
Well, welcome, folks. I just want to welcome everybody to Ryan Niemeyer's PhD defense. I want to thank everybody for coming, and this is really a busy time at the end of the semester. So I just want to do a quick introduction to Ryan for folks who don't know him. Ryan received a BS in biology from Whitworth, just up in Spokane, and then followed up with a master's basically in riparian ecology with Alex Vermeer here at CNR. And then has continued on as an IGert student in the IGert PhD focused with the sagebrush team. And so just a little bit too in terms of status of Ryan's defense. I'm actually really pleased with how things have gone so far. We were just kind of having a quick update on the various chapters, and we have one that just came back from review with very positive reviews in hydrological processes, which was really encouraging. We've had a second one come back from review in rangeland ecology and management that we're going to be reworking and resubmitting. And then there's another paper that's actually the team interdisciplinary chapter, which is now actually back in review in ecology and society. So there's 3 chapters that are moving through the system, and then a third or fourth that'll be submitted very soon. So actually, so a lot of the work I think that Ryan will be presenting is fairly mature. Some that will probably require a little bit more work towards the end, but things are really moving in a positive direction. So congratulations on all those, and congratulations on making it here today.
Yeah.
And if you could fit some lights.
I think the 2 left lights.
I think you get lights because then I can get more coffee. Yeah.
Or maybe that's the other 2.
The other two? Okay.
Yeah, sorry.
How's that?
Cool. Yeah. Can you do one more to the left? Or 2?
That one?
Or yeah.
Come on, guys, now take care of
Yeah,
it.
that was good.
Sorry. I already failed. Okay, anyway, yeah, as Tim said, thank you all for coming. I know it's kind of a busy time of year, so I appreciate you guys taking the time out. And I just want to make a note to the folks on YouTube. If you can't see the slides very well, I posted a link to my website so you can download the PDFs. So if you can't see the slides, you can go to that link. Anyway, so let's get started. So just a brief outline of what I'll be talking about today. First, I'll introduce the topic that I researched, and then I'll discuss briefly how I approached the research in my dissertation. And then I'll describe the research, and that'll be the meat of the presentation. And then finally, I'll give a few thank yous for the folks that helped me along the way. Wait, that's not the So the sagebrush steppe is an ecosystem that historically expanded from, or existed from, was current day British Columbia all the way down to northern New Mexico. And it's provided human benefits, or diverse sets of human benefits, whether it was direct provision of ecosystem services such as grazing for cows, or more indirect services just such as aesthetic enjoyment or recreational opportunities. But as you can see from this map on the left here, where the green is the historic range and the dark green is where the current range of the sagebrush steppe is, the range has decreased significantly. And there's current drivers of change that continue to threaten the sagebrush ecosystem. So one driver of change is Western juniper expansion. Both Western juniper and then other semi-arid tree species such as pinyon pine have expanded in many areas up to 10-fold throughout the western U.S. And this is just an example in southwestern Idaho. This is Flint Creek in the Oahes. And you can see in the turn of the last century, there's a few juniper dotting the kind of the ridge there. But fast forward to current day, and juniper dominate the landscape. So this is definitely a driver change that threatens the sagebrush ecosystem. A second current driver change is climate change. And as many of us know, throughout the western U.S., temperatures increase throughout the western U.S. And one of the big changes we're concerned about is a shift from a snow-dominated regime to rain-dominated precipitation regime. And Reynolds Creek experimental watersheds really documented this very well. So they started taking rain or precip and temperature measurements back in 1968. And this is a map of the watershed where blue is rain-dominated, light blue is kind of rain-snow mix, and white is snow-dominated. And so you can see just the lower part of the watershed is rain-dominated, and most of the upper part of the watershed is snow-dominated. But fast forward to current day, and most of the watershed is now rain-dominated, and just the very top of the watershed, you can see in the south end, is snow-dominated. And then so these drivers of change threaten wildlife that depends on the sagebrush steppe. So here's the iconic sagebrush obligate, the sage grouse, pictured here on the right. And with the sagebrush ecosystem coverage contracting, it also affects their habitat. So here's just a map with historic sage-grouse habitat, and then the dark green being where likely secure populations are. So these changes also threaten wildlife in the system. And then, as with much natural resource management throughout the western U.S., there's a high degree of social conflict about how the landscape is managed. And it's true for the sagebrush ecosystem as well. And to kind of just drill into an example of where this conflict is played out, this is some dialogue data from our workshops I'll talk about a little bit later, but I just want to focus in on a few quotes here. So this is in the midst of a conversation between different stakeholders, and one said, juniper take up water, and water is essential for life. So this stakeholder is saying, juniper kind of move in and basically take the water and almost take the life from the area. Whereas right after that, stakeholder 2 said, there's no evidence that juniper reduced streamflow. They're kind of saying the opposite, that juniper don't have that big impact on juniper, or on the water. And so in the midst of this, you have, in the sagebrush system, you have juniper expansion and climate change affecting the system, and then the sage-grouse being affected, and then this high degree of social conflict. With this situation, as a grad student, the question is, how do I approach these problems? How do I generate scientific knowledge that helps kind of address some of these challenges? And so kind of in I come, and this is kind of how I approach some of these challenges and try to generate scientific knowledge. And so I define myself as an interdisciplinary ecohydrologist, and which means I study the interaction between water and ecosystems. And I specifically focus on land cover change, such as from sagebrush to juniper, and climate change. And then I also, as an interdisciplinarian, focus on broader issues such as human dimensions and wildlife. And then, so with that in mind, I have kind of 3 basic approaches how I approach research. Empirical, process-based, and integrated. And I'll just define those real quick. Empirical relationship or empirical approach basically is looking for a statistical relationship between 2 factors. So here in Full Creek, they basically did some forest harvest and looked at the response to streamflow and had some statistical relationship. And so the benefit of this approach is that it's easy for managers to use. They can easily apply this statistical relationship to some situation. But there's a couple limitations. First is that this is in lodgepole pine forest, but if you apply it to, let's say, western juniper, that same statistical relationship might not hold. And another limitation is with the idea of non-stationarity. So with this system probably gets, it's kind of ballpark, but something around 80% of the precip is snow. And with climate change, if this changed to, let's say, 50%, that statistical relationship might not hold. So that's one of the limitations of this approach. So in response to this, ecohydrologists started focusing on processes. In process-based, the goal is to focus on the underlying processes that control hydrologic storage and fluxes, basically. And so the strength of this is you're really getting back to the first principles, the physics that drive these changes, and the same physics that govern gravity here, govern gravity on Mars, let's say. So you can really understand the processes. The limitations are that it requires high-quality temporal or spatial resolution data. And so here's a meteorological station where it takes hourly precip and wind and solar radiation and other data. So it requires that high quality data to actually understand the processes. And then finally, the third approach is the integrated approach. And this came out of a lot of hydrologists and other folks recognizing that human dimensions and wildlife aspects oftentimes drive watershed management and how we think about hydrology. And so this oftentimes involves collaborating with other folks in other disciplines, and it also involves collaborating with stakeholders. So kind of looks at the bigger picture. And so, and again, I used all three approaches, and there's no better or worse approach. It's just they all really complement one another. And so now I'm going to lay out a conceptual model, just how I approach these in my dissertations and kind of show where in the conceptual space my dissertation lies. Okay, so first you have watershed, a watershed scale, and you're doing empirical work. So you're looking at maybe some statistical relationship in the watershed. So that's a picture of a watershed. And then for process-based, you often zoom into the stand scale. So just look at a stand of junipers or a stand of sagebrush, for example. But through observations and modeling, you can scale that up and understand the processes at the watershed scale. So you can do process-based also at the watershed scale with modeling. So this is kind of observation modeling silo. And then the goal again is to apply it to future land cover and climate change so we can understand if the system is going to change, how the hydrology is going to change. And so you apply that to both a future stand or a future watershed. And then again, the third approach, the integrated approach, considers the human dimension and the wildlife dimension, and it often obviously feedbacks on the ecohydrology dynamics. So within this space, I'm going to kind of lay out where my different dissertation chapters resided. So my first chapter looked at snow interception in sagebrush and juniper. Is mainly an empirical study, just comparing, looking at statistical relationships between snow and interception in different, both juniper and sage. My second chapter focused on interception through fall and snowpack dynamics in juniper, and also did some future modeling in sagebrush and juniper. So this is more focusing on the processes that are going on with snow and rain interception through fall. Then chapter 3 focused on the subsurface, so looked at how both juniper and sagebrush altered the subsurface moisture dynamics. And that was a bit larger scale, so more at the watershed scale, and focused on the processes. And then chapter 4 was the integrated chapter. So we did a social ecological impact assessment. So this was more on the integrated side of this model. And then I also had a few side projects I'm just going to discuss briefly, just to kind of share some of the other things I was doing. One of the projects was the climate indicators project that some of you in this room were in. And I was looking at snowpack across Idaho, and so it was more at the watershed scale. And there's also a social survey where we looked at what were the most important indicators for managers in Idaho, and that's why it's pointing to the social ecological. And just kind of share one of the important things for that was that water was one of the most important indicators. So as a hydrologist, I was pretty happy with that. Another side project was looking at pinyon juniper cover change and how the potential to increase groundwater recharge changes with the different climate, whether it's a monsoon or Mediterranean. And that's more at the watershed scale and focused on the processes. And then finally, as part of a Northwest Climate Science Center doctoral fellowship, I looked at tree drought vulnerability in kind of 2 end-member stands. I was looking at dry aspen stands in Idaho and then more wet conifer stands. Now, I would love to present on all these things, but I'm sure you're going to get hungry. It'd probably be like 2 o'clock by the time I got through. So I'm really going to only focus on chapter 2 and 3 and unpack the process-based work with juniper both above and below ground, then talk a bit about the pinyon juniper cover across the western U.S., and then finish up with the integrated chapter. And then I also want to mention too, I was part of the IGert doctoral fellowship, and the fellowship basically puts us in teams with different folks in different disciplines. So I was an ecological, there was a restoration ecologist, a wildlife ecologist, and a rural sociologist. So a lot of my thinking about how to do research was done with this team. And then chapter 4 was, we all did this as a team project. So just to kind of give you some context. Okay, so chapter 2, looking at interception and through fall and snowpack dynamics in western juniper. And so for this project, I had both a field-based component where I looked at mainly juniper and interspace dynamics, and then I had a modeling component where I looked at both climate change and vegetation change. And so I'm going to talk first, just to lay it out, I'm going to talk about the fieldwork methods and results, and then talk about more the modeling methods and results. So let's kind of couch it that way. So again, this is at the more at the stand level and looking at the processes. So again, back to that climate change piece. So we're shifting, and we're still shifting from snow-dominated regimes to more rain-dominated regimes in much of the sagebrush steppe. And the question is, how does this change above-ground dynamics? So through-fall, interception, and snowpack dynamics. So that's kind of the main question for this chapter. And this work was carried out at Reynolds Creek Experimental Watershed in southwestern Idaho. Since I wanted to have quite a bit of snow and rain, I had to go pretty high up in the watershed. So the star there is where my site was located. And I should also mention this is run by the USDA ARS out of Boise. So for the field methods, I had a couple of different methods. First, I set up lysimeters, 2 lysimeters under trees and 2 in the interspace, and that's just you can see that basically it's tarped plywood and it funnels to a buried tipping bucket, so you know how much either rain or snow melt occurs in a given hour. And I set up PVC snow stakes and I had an automatic camera measuring snow depth basically every hour. I'd take a picture and I could then get the snow depth from the photo. And then we also, although it's only 2 trees, and especially my ecologist friends are kind of like, that was kind of a running joke, like 2 trees. But to understand if those 2 trees represent the entire stand, we did snow surveys across the 2-acre stand to make sure that the snowpack dynamics under those 2 trees actually represented across the 2-acre area. So I'm going to drill in just to a few plots, and this is one of my more information-dense plots, so I'll walk you through it. So this is, we looked at through fall, and through fall is just the ratio of snow or rain under the tree compared to outside the tree. So if you have a through fall ratio less than 1, you're going to have more rain or snow outside the tree than under the tree. If it's greater than 1, there's going to be more rain or snow outside the tree than under the tree. And that probably doesn't make much sense, but in a couple slides, I'll start to make sense in a second. And then, okay, so that's the y-axis. The x-axis is gross, either precipitation or snow melt. And for the diamonds there, that's from the snow survey. So those cameras, we were able to look at snow depth before and then after the snowstorm, so measure how much the snow depth changed. And for the circles, that's the lysimeter data. So we have for storms, blue is for snowstorms, gray was a rain-snow mix, and then red was for rain. And so looking at this data, if you just focus on the lower part of the graph, it makes sense. You know, this is, as hydrologists, if we have a through-fall plot, this is what we'd expect. You have if you have little precip, you don't have much through fall, and as you increase and you get larger storms, you're going to have more through fall. This all makes sense. And also notice that rain and snow are actually pretty similar too. And then also you get kind of this, it kind of peaks out and flattens out as the storms get larger. And this is, again, what we'd expect. So just looking at this part of the graph, it makes sense. But then the question is, what's going on up here? And how can you have more snow or more through fall under the tree than outside the tree? It doesn't really make sense because the tree's going to intercept snow or rain. Well, something we observed is that when we looked at the camera data closer is that tree wells would form under these juniper trees. Many of you skiers have experienced these tree wells. You'll see basically around a trunk, you see the snow kind of decreases, kind of a cone of depression in a way. And we observed this in the juniper as well. So this picture, let's see, February of last year. So the yellow strip there is 50 centimeters, and each kind of candy cane stripe is 5 centimeters. So if you count down, the snow depth's about 30 or 40 centimeters in the interspace. And then if you look at under the tree, you can't really see the yellow mark there, but I know that it's there. You can see that it's either no snow on the right there, or maybe 5 or 10 centimeter snow depth. So there's quite a bit of a tree well formed there. And then again on the south side of the tree, it's bare for much of the area under the tree there. So how does this change through fall dynamics? Well, so here we plotted through fall, so it's the same y-axis. This is just snow depth. It's not rain or snow melt. So through fall is same on the y-axis, and then the x-axis is the difference in snow depth between the interspace and the tree. So if you have 0, that means the snow depth is the same between the tree and the interspace. Or if it's 30, the snow depth will be 30 centimeters lower under the tree than the interspace. And basically you see an increase in through fall as you have an increase in tree williness, you could call it. Basically, increase in difference of snow depth between the tree and the inner space. And so that relationship was statistically significant. Obviously, there's some noise in that data. One of the main things is that I didn't show a plot of this, but basically you need to have a really dry storm. So if it's a wet storm, the snow is wet, and once it falls, it stays in place. It doesn't blow around. You need to have a windy storm too. So if the wind's not blowing it around, it's not going to blow it into that tree well. So that's where some of that noise of that data comes from. Okay, so just kind of in sum, just from this field component. So basically, snow and rain through fall isn't that much different, although there is this preferential deposition of snow underneath the tree when these tree wells form. In our first water year, this is about 15 centimeters of extra snow depth based on that previous linear regression. In the second year, it was about 13 centimeters. And these are both low snow years too, so that number would increase if we had a larger snow year. So, okay, so now I'm going to go to the simulation component. So the goal of this is looking at, so if we have juniper and sagebrush cover change, both from juniper expansion or there's a lot of juniper removal going on in the system, and we have climate change happening on top of that, how do these two kind of drivers of change affect future above ground dynamics? And so we use the simultaneous heat and water model developed by Gerald Fleshinger out of the USD ARS, and he's also an author on this paper. And it's just a one-dimensional model, runs on hourly data based on solar radiation, wind, temperature, precip, and relative humidity, hourly data, running the model, runs an hourly time step. And we use for climate forcing data, we use the multivariate adaptive continuous analogs, or MACA data set that John Obosicle here at UI and some other folks have developed. And we took the historic data, so the measured hourly data from 2007 to 2014, and then we looked at the future projection under mid-21st century under RCP 8.5, which is basically kind of a future CO2 scenario, business as usual, kind of no large curtailing of CO2. And we looked at, for that future data set, what was the monthly temperature increase? So if it was 3.1 degrees Celsius, we took the historic data set and just applied that 3.1 centigrade increase to the historic data for the future data. So just did a temperature increase, basically. And on average, across the months, it's about a 3 degrees Celsius warming from current to future. And we also, again, did scenarios with juniper, mountain sagebrush, and low sagebrush. And Shaw's been running all these vegetation types. Gerald's run them across Reynolds Creek, so it's the model parameters are pretty well tested. So I'm just going to show you a few of the graphs. So the first I want to show you is the snow water equivalent. Snow water equivalent is just if you take the snow and melted it, and that would be your kind of depth of water from the snow. And it's SWE for short. And so that's the y-axis. The x-axis is just the average SWE through time, so through the winter months. And the dark lines, the dark solid lines are current simulations, and the dotted lighter lines are future simulations. And what we see here is that there is a difference between mountain sage, which is brown, and juniper, which is what we saw in our measured data, that the snow depth was shallower under the juniper than outside the juniper. But what's interesting is when you look at the future scenario, that difference all but disappears. You know, the snowpack is much lower, only averages about 50 millimeters of SWE, and there's little difference between the juniper and the mountain sagebrush in the future. And then the other thing I wanted to focus on for this presentation was surface water input, or SWE for short. And so I'm basically comparing across climate, so current and future, and then across the three vegetation types. And a couple of patterns emerged. The first was that looking at the total surface water input, so just the amount of water that enters the soil. Between the current and future, we don't see much change in the amount. So it's a slight decrease, but not a significant amount, and that's across all vegetation types. But if we look across vegetation types, we see that within each climate scenario, there's as you increase in basically LAI, or vegetation density, you see an increase in surface water, or excuse me, if you decrease your LAI and your vegetation density, you increase your surface water input, which makes sense. You have less interception occurring, that sort of thing. So that's what we saw for the SWE amount. But for the timing of SWE, so the SWE 50% day is basically the day that half of the surface water input occurred in a given year, one being January 1. We see kind of the opposite, that same vegetation across climate, we see a much earlier surface water input 50% day. So for juniper, for example, 178, that's middle to late May. 132's middle to early April. So we see basically shifts to earlier under future climate. But across vegetation, we don't see much difference across the different climate scenarios. So you look at, for the current, it's within a week of each other. In the future, all the vegetation types are within a week of each other. So basically, vegetation more affects the amount of surface water input, whereas the climate affects more the timing of the surface water input. Chapter 3. So for this chapter, I was looking at basically the moisture dynamics underneath juniper tree sagebrush continuum. So in the conceptual model space, this is kind of between the stand and the watershed scale. And I was focusing on the processes here. So I had two main approaches for this project. And again, the question is basically, how does Western juniper alter subsurface dynamics compared to sagebrush? That's the big question. And so the first approach was I had soil moisture probes installed next to 4 trees. And there was 4 installed at each tree. 2 were at 15 centimeters, both under the tree and outside the tree. And then 2 at 60 centimeters under the tree and outside the tree, just like that picture shows. And then I had 2 trees in the more dense, folks would probably call us, if you're familiar with the juniper expansion terminology, a phase 2 juniper expansion. So you can see the 2 blue dots where it's located. And then the 2 blue dots in the northern part of the plot are where the other 2 trees were, and it's more a phase 1 juniper expansion, so more of a savanna-like, more open. So that was for the first method. The second method was with what's called electrical resistivity tomography survey, or ERT for short. And we basically stuck metal rods along about every meter along a 100-meter transect. And the red dotted line is where the transect was. And we made sure to cover both the high-density juniper, so more on the southern part of the transect, to the more low-density juniper, more savanna-like in the northern part of the transect. And we did this in the wet and the dry season. And basically, I should mention too, the ERT basically shoots electricity through the ground. And we all learned, in the bathtub, you don't want to drop your radio in it because it'll electrocute you, because water conducts electricity. So if it's more wet, the electricity basically goes faster. And if it's drier, it won't go as fast, is kind of the basic concept. And so you do a wet season measurement. So we did a May measurement where most of the soil moisture is still there. And then we did a dry season measurement in August. You can see it's pretty dry. So less moisture is there. So you can subtract those 2 and see where water was pulled out of the ground by vegetation. Oops, I thought that was a computer. Okay, so the first plot. So again, I'm just going to focus on a few main plots. And the first thing I want to note too is between the low and the high density juniper. So the left picture is the high density juniper, and the right picture is the low density juniper. So just looking, you can kind of visually notice. I want to give you guys a second. So you can visually notice that there's much more sagebrush in the low density juniper compared to the high density juniper. And this has kind of been documented throughout Western juniper expansion. When it expands to some density, you see less sagebrush. And so what we noticed was interesting, that we compared just across trees at the 15 centimeters. And I should back up for a sec. So our first analysis for this was after a given rainstorm, we looked at change in water content at 15 centimeters, both under and outside the tree. So you had some water content, you had a rainstorm, and saw how it changed. And at 15 centimeters, we just pooled all the data, looked at canopy versus interspace, and we didn't see much difference. But then we broke it out, looking at the 2 trees in the high-density juniper compared to low-density, and we saw a clear relationship. So this is kind of information dense, so I'll walk you through it. So this y-axis is basically the change in the tree water content after a storm minus the change in the interspace water content for that same storm. So if it's above 0, you had a greater change in the water content in the tree or under the tree. If you had it below 0, it was greater change in water content in the interspace. And the blue dots, again, are the high density juniper, the yellow triangles are the low density juniper. What we see here is, and this is total storm precipitation, so small storms, larger storms. What we see here is that for the lower storms, there's not much difference between the 2. They're almost both the tree and the interspace increase about the same amount on average. But as you increase in storm volume, you see that for the higher density juniper, there's a greater increase under the tree, whereas for the lower density juniper, there's a greater increase in the inner space. And at first this seems odd, but when you think about it based on processes, it makes sense. Kind of taking a step back about 20 years, hydrologists used to think that when infiltration occurred, it occurred in an even wetting front, so water would infiltrate the soil kind of at the same level. But what hydrologists discovered was that preferential flow paths would occur, and preferential flow paths are basically the water takes the path of least resistance. So if there's a wormhole or a root, the water will follow that preferentially. It won't kind of go with the wetting front. And some of my, I just mentioned my master's work, we did some of this work. We actually put dye, we let all this non-toxic dye, and you can actually dig it out and see where it followed. And there's these little fingers that extend if it's a room hole or a wort or whatnot, or a root or whatnot. And so for a tree, this makes sense. You have a tree, it's got a lot of roots, so water is going to follow that root because it's a nice little highway for it to follow. So it makes sense, but why is there a difference between the high density and low density juniper? Well, as you can see here, there's very few sagebrush in the inner space for the high density juniper. And so there's basically not a lot of little straws in the ground for the water to follow. But if it's a low density juniper, you can see there's much more low sagebrush. There's more little pathways for the water to follow in the inner space. So basically, if you have high density juniper, there's more infiltration under the tree at 15 centimeters compared to the low density juniper. Okay, so this is looking at the 60 centimeter data. So this is the same analysis. So we're looking at before a storm and after the storm and how water content changed. And this is the same, so that's the change in water content. And this is the same x-axis. This is just total storm precipitation. And then I also covered the points based on the storm intensity. And then circle is for canopy, triangle is for the inner space measurements. And first thing you notice is that most storms, you don't see a change in water content, which makes sense. 60 centimeters is pretty far down. You need a pretty heavy rainstorm to actually see an increase in moisture there for that storm. But you notice is that when there is an increase in moisture, it's almost exclusively under the canopy. So you see circles here, which again was kind of not what we hypothesized originally, because you'd think that if it's below the tree, you'll get rain interception, so you'd see a greater increase in the inner space. But again, thinking about the preferential flow path mechanism, it does make sense because below the tree there's all these roots, and so the water, even though maybe less water is actually initially hitting the ground under the tree, there's more of those pathways for the water to follow and to get down deeper. So, and this was statistically significant for, we had these non-parametric statistics, but the canopy was statistically different than the inner space. Okay, so now to the ERT survey aspect. So this is kind of a dense or information-rich slide, so I'll kind of walk you through it. This is basically looking at a kind of almost like when you have those glass anthill views. It's looking at a cross section of the ERT transect. And this is the elevation, so it's in meters. So 0 here, this is negative 12 meters. And so vegetation's on top, so we did a vegetation survey. And the triangles are juniper trees. And if it's darker green, it means it's right on the transect. If it's more yellow, it's further away from the transect. So this tree is right on the transect. This large tree is about 3 meters off of it. And then you can also see where the higher density sagebrush. So you can see right here, there's more sagebrush, which makes sense. That was the lower density juniper, so there's more sagebrush. And then we also did a seismic survey, which basically tells you what type of subsurface is at and what depth. And so this brown line is the border between soil. So above this ground line is soil, so it holds more water. Below that is saprolite, which is basically unconsolidated material and mixed with bedrock. And I should mention too that the subsurface was basalt. So this is all saprolite. Holds some water, not a lot of water, and then this is just broken up basalt bedrock right there. So again, up here holds more water, holds less water here. And then this colored is the difference between the May and the August ERT surveys. And basically what you see is if it's red, it basically dried out more, and if it's white or blue, it didn't dry out as much. And kind of the pattern that we see here is that, well, first off, we see this large tree that's right in the transect. A lot of moisture was taken out up to depths of 12 meters. And then we also see where there's more juniper, for example, here next to this big clump, and then here, more moisture was taken out. Conversely, areas where there was less juniper, such as here, this is an open area, and then here, this open area, there's much less moisture taken out of the subsurface. And again, just want to reiterate too, this was kind of surprising for us because, again, this is up to 12 meters, so moisture is being taken out. I mean, 12 meters, that's over 30 feet. So that's a pretty far down, which is pretty surprising. Okay, so just kind of some conclusions from those 2 process-based chapters in Juniper. So this is kind of a conceptual Juniper ecohydrology model. So first thing we observe is that through fall between rain and snow wasn't that much different. But because of tree wells, there's a preferential snow deposition underneath the tree. And then we observe too that there's preferential infiltration, especially at deeper depths below the tree because of the roots. And then finally, the juniper is able to both increase infiltration deeper and then also draw out moisture at deeper depths than sagebrush vegetation. So this is kind of a picture of how the juniper is basically able to be really successful in these semi-arid systems. Okay, so this is just that project, the Western U.S. wide scale. I'm not gonna do that kind of full methods presentation because I don't have time, but I just want to kind of give you a little snippet of it. So, yeah. Okay, so in conceptual space, this is at the watershed scale. We're focusing on the processes. Okay, so this map is where there's any color is where a pinyon juniper cover is based on the USGS 2002 map, and it's mean annual precipitation. So you can see the drier areas are around 200 millimeters, wetter areas up to 1,200 millimeters. And a study by IGert in 1983, based on some historical data, basically posited that 450 millimeters was the cutoff in a semi-arid area where if you remove the woody vegetation, you'll see an increase in stream flow. So based on that, about half of this coverage, you'd see an increase in stream flow if it's pinyon juniper cover, let's say. And so that was that study. But there was a study in the meantime that was at Beaver Creek in Arizona and also Cervical Ridge. You can see the BC and the CR there. And they showed that after, Beaver Creek specifically showed that after pinyon juniper removal, there's only a 9.7 millimeter gain, area weighted for that 7 years, and then the increase disappeared. So, and that was in a pretty wet area. It's about 700 millimeters of precipitation. So many have posited that if you have a pretty wet area where you're not seeing a appreciable increase in stream flow, how would you expect it anywhere in Idaho or Oregon, for example? But one major difference between Arizona and the Northern Great Basin, as we know, is the monsoons versus the Mediterranean climate. So this is a picture, same coverage, but of the monsoon index. So monsoon index is just the amount of precip that occurs in the summer months, in July, August, and September, over the total precip. So again, as we all know, as we all experience, we're what's called a Mediterranean climate. The precip occurs when it's cold, doesn't occur when it's warm. So you see it's pretty, very few precip occurs in the summer, again, in Idaho, Oregon, northern Nevada. But in Arizona, New Mexico, much of, if not the majority of the precip occurs in those months. It's a very different climate system. So the question was, with these different climates, when you have pinyon juniper cover change, go to the next slide. When you have this pinyon juniper cover change from a semi-arid tree to a grass or a forb or even just a low sagebrush, is there going to be differences in groundwater recharge across these different climates? And so I'll just briefly describe, I basically used a model developed by a Swedish scientist called HBV, and I used 30 years of prism data, daily prism data to run the model, and I just compared tree vegetation compared to grass vegetation. I looked at groundwater recharge, so just water that got past the root zone. And the comparison so this graph this map is groundwater recharge from the grass minus the groundwater recharge from the tree. So how much gain in recharge do you get if you remove the vegetation? And what we see is the map really follows well with the monsoon index. So areas where there's high monsoon index, so most of the precip occurs in the summer, you see very low potential for increase in recharge. So something like 20 millimeters, let's say, so pretty low. Whereas in the Northern Great Basin, where there's a much lower monsoon index, little precip occurs in the summer, most occurs in the winter, much higher potential for increase in groundwater recharge with vegetation change. So, and we plotted some of this up, and basically amount of precipitation and the timing of precipitation are both important in determining if you'll see a gain in stream flow. And just to cycle back to my social conflict side, back in the beginning, I actually talked to these folks after the data had been collected. We were just kind of talking shop after. And not to be a total cop-out, but I basically told them that they're both right. That stakeholder one's right in that juniper do matter, they do affect the water, and especially in the Northern Great Basin with more Mediterranean climate, it does. But stakeholder two is also right because based on, there's no kind of measured empirical studies that actually show that pinyon juniper cover removal will increase stream flow. And it's mainly because, as I mentioned, the main studies that have looked at this actually measured it in a catchment is in Arizona, New Mexico, and Texas. So it's kind of an impetus for more research. And actually, USDA ARS out of Boise's instrumented 4 catchments in the Oahes, and they're going to cut down juniper, I think, in 2 of them pretty soon. I think in the next year or 2. It's undergoing NEPA right now, so kind of stay tuned for their results. But I imagine, based on my simulation work, they'll actually show an appreciable gain in strength flow, but we'll see. Okay, and I just want to mention too, University of Idaho, as Idaho's land grant research institution, part of that kind of call or challenge is to do science that benefits the people of Idaho. And I took this seriously as a graduate student, and so I did various outreach events. One of them was I did a 2-day outreach event. The first one was I shared some of this research with some BLM managers in the Boise district. And then I did a second day, the next day, with the Nature Conservancy in their Boise office with a group of about 20 folks from Trout Unlimited, NRCS, Nature Conservancy, and some other organizations. And then I should also mention Tim Link did some outreach with NRCS in Oregon too. So we're kind of actively sharing this with stakeholders who can actually benefit from this knowledge in their management work. Okay, so now to the chapter 4. This is a social ecological impact assessment. And so I just want to give a little bit more context for the reasoning for this project. So the National Environmental Policy Act passed back in '69 basically said, the law says that for any federal land use action, so any land use action, land management action on federal land, so BLM, U.S. Forest Service, it has to consider impacts on both humans and the ecology of the system, basically. And which is, I mean, it's a good idea. You know, it's good due diligence to think if you're going to do some land management action, you should know what the impacts are going to be. But what happens is that both these institutions are pretty ecology heavy. There's only a small percentage of folks that work there that are actually social scientists, and so these impact assessments, when they come out, tend to be more ecology heavy, not as much socially focused. And when there is a social impact assessment, it's often more of a technical assessment. It'll use, for example, Census Bureau data to run some model, for example. So our goal with this project with the IGert Sagebrush team was to develop an integrated social ecological impact assessment that could look at both the social and the ecological impacts. So this, again, in the conceptual space, is in the integrated side. So this is our conceptual model. We basically merged ecosystem processes paradigm and then a social processes paradigm. And you basically have an intervention, and then you'll have some ecological change or social change, and that'll cascade down. The ecological change will cascade down to an ecological impact, which will affect humans, or the social change will affect humans. So I'm going to give a couple examples for how this plays out. So for juniper removal, that's the intervention, and this is just a potential impact. You'll have reduced juniper cover, improved wildlife habitat, and then maybe it's a positive physical experience because it's improved hunting. So this person, because of juniper removal, maybe you'll experience positive experience because of improved hunting. Another potential impact would be if you have juniper removal, maybe you have litigation that occurs because of that prevents juniper treatment. No juniper treatment occurs, increased juniper, and then maybe that's a positive physical experience because increased bluebird habitat, because bluebirds use juniper. So maybe someone who likes bluebirds, you know, that's a benefit. And again, these aren't just all positive. You can have negative impacts or kind of you know, no significant change. But that's just a couple examples of how this conceptual model works. Okay, so we didn't want to just develop this, but we want to actually apply it to a kind of real world situation. And so we applied it to the Bruno Oahe Sage-Grouse Habitat, or BOSH project. It's run by the BLM, and they're going through the NEPA process as we speak. And the goal of the BOSH project is to improve sage-grouse habitat. And what they did is they basically looked at, I think it was the active leks, I think it was 63 active leks in mainly the Oahe County area, and drew a 10-kilometer buffer around those. And the plan is to remove any low or medium density juniper in that 10-kilometer buffer. And the idea being that, so one of the main predators of sage grouse is predatory birds. So when they see a large object, you know, taller than a sagebrush, they get kind of scared, like that might be a falcon or something, you know. So that's why they want to move the juniper, so to improve the sage grouse habitat. And so you can see the hatched area in the buffer. That's the total treatment. It's about 1.75 million acres. And then just for context, that star is where Rounds Creek's at, so it's kind of in the middle of that potential area. And so they had 3 proposals for this project. The first one, like anyone, is no action, so don't do anything. The second one is use a full suite of tools they're proposing to use. And so the 3 tools they proposed were cut and scatter. So you basically cut down the tree, and then if you have some branches, they'll cut those too, and they'll scatter those branches. For mastication is the second tool. So it's just you kind of take a bulldozer with this rotating thing that just kind of grinds the juniper down to a pulp. And then the jackpot burning, where you basically pile all the juniper up, and then when it's cold, you burn the pile. So that's a full suite of tools throughout the project area. And the third option is just cut and scatter. So don't use any of these more intensive management approaches, but just do cut and scatter throughout the area. And then those symbols you'll see in the graphs later, those symbols will correspond to the no action, full suite, and cut and scatter. Okay, so we had two groups of stakeholders. The first group was established by the BLM. It was a pretty diverse group of folks. It included NRCS, NRCS, Nature Conservancy, folks from the state of Idaho, and some BLM folks, pictured here on the left. And then our second group was a group that we put together and included some private ranchers, people from the Audubon Society, Idaho Conservation League, and president of a local ATV club. And so we had two groups, and we wanted to do two separate workshops for each group, so we ended up having 4 workshops total. In the first one, we wanted to use that conceptual model, and we first did questionnaires and looked at different aspects of that conceptual model, what are the different impacts. And then we had dialogue after that to really unpack, what were the actual linkages, if was it through the social side or was it through the ecological side, for example. I'm not going to get into dialogue day to day just because I don't have time, but I'll show a few of the questionnaires responses. In our second workshop, we recognize that with many issues in natural resource management, it's inherently spatial. And so we wanted to do what's called public participatory GIS. So where are people's values and impacts across the landscape? And so we basically asked people, where do you value ecological aspects, social aspects, or economic aspects? And we had them basically draw. You can see one of the stakeholders drawing there. So that's basically what we did. And I'll show the final map for that as well. Okay, so this is for the questionnaire surveys for that first workshop. And we had 20 total respondents between the two groups. And for this, we asked, if there's a 0, they rated 0 is as bad as it can get, and 10 is as good as it can get, so they rate between that. And then they would rate it for each, the no action, full suite, and cut and scatter. And so for this question, it's for the future economic activity. So how will these different options affect the future economic activity of the Oahes? And for this question, we saw a pretty consistent trend that most folks rated the no action as worse, as not quite as bad as, well, some for as bad as it can get, basically worse for the no action compared to full suite and cut and scatter rated better. So this is pretty consistent across the 20 respondents. But for the question, the ability of the Oahes to provide opportunities for spiritual, aesthetic, and recreational enjoyment, this was kind of a mixed bag. That some respondents, for example, respondent 4 rated the no action was a 10. Was no action would be as good as you can get for them for this aesthetic, spiritual, recreational aspect. Whereas no action, cut and scatter would be much worse. Whereas you go and look at maybe response 6 here, they rate the cut and scatter and the full suite as much better than if there was no action. So kind of a mixed bag of impacts for this question. And then finally for the second workshop, we had them draw their social, economic, and ecological values, but this is just the merged map. And for social values, some of the sites were people noted were Silver City. So it's an old mining town, so people really valued that from kind of a social, cultural perspective, as well as some Native American kind of cultural sites that people noted. For ecological values, people oftentimes focus on the rivers. So here's the Oahe River, and here's the Bruner River, which again, as a hydrologist, I was pretty excited about. But ecologically, it was important just for habitat connectivity and aquatic life and biodiversity in general. And then economic values were kind of mapped more broad spatially. So someone would almost circle the entire map and say, I value this whole area for grazing, for example. So it was more broader values signified. Okay, so that's the end of my research part. So I'm just going to have a few thank yous. With any PhD, it's easy to go down a few rabbit holes, and I just want to thank a few folks that kind of help keep me on the straight and narrow. So first, I want to thank my IGert team, including Joe, Amanda, and Alex, as well as our team leader, GD. They made the experience enjoyable both professionally, just kind of building off one another and learning from one another, but also just personally, they were some of my best friends throughout this experience. So big thanks to them. I also want to thank my wife, Becca, And I just went for her emotional support. And I want to say it was serendipitous that I met her within 3 months of starting the IGert, because a lot of the lessons I was learning in IGert, actually in this very room, quite lessons like teamwork, how to do teamwork, how to listen to someone from a different perspective, how to stick with the project even if you're frustrated with each other. I also was learning in my relationship with Becca, so they kind of fed off and built on one another. And then also I want to thank my committee, my advisor Tim, my committee JD, Mark, and Robert. I just felt super blessed to have them both to kind of shepherd me through the experience. And I always felt that they had my back and they had my best career interests at heart. And I feel I'm definitely a product of just a lot of their mentoring. So I really appreciate the support they've given me. And then I also want to thank my lab mates in Tim Link's lab, both Zion and Sage, and who can forget our lab mascot, the Labradoodle Magruder. So they all made time in lab a lot of fun. And then finally, this is the shotgun blast slide. Thank everybody else. Like, you don't have time to thank you. Folks who helped me in the field, my family and friends for their support, and also the folks in the greater Moscow community, whether great faculty and other grad students here, folks in the wider Moscow community, such as folks from Moscow First Pres, John's Alley, the co-op, all those great places. They've all made the PhD experience really joyful. So, and then last but not least, I want to thank the financial support from the NSF IGert program, which supported about 3 years of doctoral fellowship, and then also the USGS-backed Northwest Climate Science Center, which supported me for a 6-month doctoral fellowship. Also for 2 small team grants for our teamwork, the Idaho Governor's Office of Species Conservation and the BLM. And then finally for field and institutional support, University of Idaho, the Rounds Creek Ecological Zone Observatory, which is run by the USGS. So with that, I'll take any questions and thank you.
A few more, probably 10 minutes or so for questions. I'm going to keep mine for the closed door session.
Cool.
So, invite anybody else to ask.
No, Sanford?
So what's your impression of how the managers can use the chapter 2 and 3 results that you have been shown?
Right. So I would say, and I didn't talk much about this, but with that increased snow deposition, I would think under future climate change, there is a chance that interspace plant species, so whether grasses and forbs or sagebrush, might be a little better off because you don't have that snow preferential deposition. Although that could be kind of canceled out with the increased evaporative demand, so it could be a wash. So there's one thought that just to think about with climate change. I would say that, and this kind of confirms other research, that when you go from that lower density juniper to higher density, there's almost a phase shift where once you have fewer of the sagebrush in the interspace to focus that infiltration, you'll have much less water in the interspace. So it's almost this phase shift between low and high density. So basically, if you're trying to restore to a sagebrush system, get it while it's still lower density before it kind of shifts to much higher juniper density. So
That'd be your advice to them.
Mhm.
And have you had reactions
yeah, I mean,
from them that like that or similar?
yeah, I mean, so I've done outreach and definitely folks from the BLM and NRCS like to hear about it. I don't know if I've heard specifically like, oh, this information is really helpful for this specific situation, but I think a lot of it too confirms that there's a lot of anecdotal evidence that juniper take up water and affect the soil hydrology. So it's kind of actually measuring and quantifying those effects.
So did you have burrowing animals out at these sites and any, do those affect your water infiltration?
Yeah, so I didn't necessarily look at burrowing animals, although I did have rabbits. I saw some, I think, jackrabbits out there. I don't know if I saw any burrowing ants, but some interesting thing, this is total anecdotal, but Mark and I were there for one of our snow surveys. There was a melt event, and there was there was a lot of overland flow, and a lot of it was actually coming out of burrows. So it was like on a hill slope, and there was a burrow, and there'd be like water actually that infiltrated, and that was like coming out of these burrows, which is I got videos if you want to see it, but it was pretty wild. But I wasn't necessarily looking at that kind of larger spatial scale of runoff and that sort of thing. But definitely saw an effect just from that, just anecdotally witnessing that snow melt event. So.
I'm kind of curious about the relationship between the hardcore scientific data.
Mm-hmm.
And the point is to try and make our world better scientifically, but you've got the balance of the social aspect. You know, my question, I guess, is strategies for dealing with the emotional end, which is the social, to get to the scientific application.
Right. So I think what you're asking is, so there's like chapters 2 and 3, which look at the processes, and then how do people respond to that? You know, if Juniper take up more water, for example, and
How to navigate.
yeah. So that's a great question. So for our chapter 4, our social ecological impact assessment, we're just looking at how people respond to that. You know, do they say Juniper take up a lot of water? Do they say it doesn't matter? Or do they say Juniper good for bluebird habitat? We're just kind of more trying to, through social methods, quantify their response to that. So we're not necessarily trying to, especially as scientists, kind of steer them in one direction or the other. We're just trying to kind of quantify how they do respond to that. So
Does that make a difference?
I mean, it does. It's part of the NEPA process. So I mean, just for any federal management action, you need to see, you know, if you remove a bunch of juniper, does it affect people socially, and then does it affect the ecology? So actually quantifying that's important. So yeah, good question. That's a tough issue, but it's a good question.
That social ecological piece, and also the NEPA process, was there also discussion of whether this would become more or less salient if sage grouse become listed species? And because we're right on the cusp of that.
Right,
We're
right.
looking at listing, ESA listing sage grouse. So
Right.
did you hear any of that in these
Yeah, and
discussions?
that's a great point. Actually, I was going to mention, but I forgot to. So, but we did this before the September decision. So this is definitely a big concern that this was going to be kind of a game changer. And then yeah, so now it's, as I understand it, correct me if I'm wrong, but it's not listed. The Department of Interior decided not to list it, but there's still, you know, obviously contention around it. So, I mean, I think the hope is just to more quantify what the social impacts are. Like, how do people perceive if the sage grouse was listed, or if they did this juniper treatment? That's kind of the goal of especially chapter 4, to actually quantify that. Like, how do people actually think that they'll be impacted? So, I'm not sure if I answered your question there.
That was just sort of the curiosity whether in these sessions, whether you heard that also.
Oh, for sure. Yeah. Oh, yeah. Definitely heard a
And
lot
whether
about.
that was impacting the answers that people were giving.
Yeah.
Could that be confounding effect to their?
Right. Yeah. Yeah. And I'd be curious to see what they would say now. Although, again, I don't think it's resolved because of the decision, but it definitely can't. I don't remember off the top of my. We kind of coded our dialogue data, so I don't remember how many times the ESA was mentioned, but it was definitely a big factor. So.
Thanks.
Just to pick the hang over that. I come from shark tip country, which has already been through that, going through it. So there's lessons to be learned.
That's right.
Steve.
Fire. So I know that wasn't part of your experimental design
Yep,
or
yeah.
your process.
Yep.
Can you just make a couple of statements about the interaction effects of fire on what you were working on?
That's great.
What are the dominant things we should pay attention to?
You know, and so the first sagebrush slide, maybe the question was, wait, why did the area contract? And that's basically one of the huge things with fire. So juniper are very oily tree species, so they burn up really easily. And so kind of historically from different paleo methods and other methods, they knew that juniper typically stick to the ridge tops where it's rocky and there's not as much grass to burn up. So basically areas where there wasn't as much burning, and they would kind of expand down slope, and then they burn much easier than the sagebrush, and then they retract. So that's like fire was kind of basically controlling their expansion before. But you know, same with forest, same with sagebrush, we've been putting out fires for the last 100 years. So they're kind of allowed to expand unchecked, basically. And it's partly an ecological niche opening up with grazing too. So kind of the grazing opening up the ecological niche and taking fire away from the system, they're expanding quite a bit. But the tricky thing with that is your response might be, well, let's just reintroduce fire. But with cheatgrass, that kind of confounds that because they've observed that they'll let a fire will sweep through a juniper area and cheatgrass will move in instead of sagebrush. So it's kind of not that simple response. But yeah, that's definitely going to, especially with climate change, continue to play a factor.
And it's fair to say that then the fire gives the juniper the advantage, and then the more mature and established the juniper is, the more advantage they take from that, right?
So I would say it gives the sagebrush the advantage.
The sage, right? So,
Yeah.
but if the juniper is established and becomes more mature, it's actually gaining. It's got a non-linear influence.
Well, it's definitely, if it gets to that high density, there's no sagebrush around, oftentimes you won't have any source seed and they'll just cheatgrass will come back. So it's definitely.
Right, plus the grabbing of additional water because of its morphology.
Right, yeah. So, but yeah, fire is definitely a big part of the story here.
Yeah, I just want to ask a
Sure.
question that related to the social questions as well.
within the groups that you surveyed and interviewed, did you have an indigenous perspective at all? Because I was just thinking about some of the other IGert students, Cody Davis mentioned how juniper actually is sacred to some of the indigenous people
Yep, yeah.
in that area, more to the east. But anyway,
Right.
What was that? Did that perspective come up at all?
Yeah, that's a great point. I'll just repeat what you just said. I don't know if folks heard that. Yeah, so some of the folks I know, like Shoshone-Bannock tribes, actually see juniper as sacred. So there's kind of, and I believe, I'm pretty sure I've seen Shoshone-Bannock still do juniper treatment too. So I don't know the exact kind of social dynamics, but it's still a sacred tree to them. And we did actually elicit participation from them, but they basically see themselves, I mean, they are a sovereign nation, and so they, interact with the BLM as a sovereign nation and not necessarily through us, because we more had agencies participating. So I think, they are a sovereign nation, so they don't necessarily interact with us on the same level that, Nature Conservancy would. So we definitely wanted to, but it just wasn't kind of in the cards for what we were doing. So, yeah, good question.
Okay, we're right about noon, so I think I want to kind of wrap this up and to say thanks again to Ryan. And just another quick follow-on is when I introduced Ryan, I sort of did the retrospective story of Ryan's life, and just to sort of say the prospective of where he's going. Ryan's got himself a great postdoc that starts right after the first of the new year at the University of Washington. And what's kind of a neat feature about that was the person who's hired Ryan for the postdoc really viewed the IGert experience, and in particular the team-based work, as one of the huge benefits for that, because it's a project that includes an ecological, physical, and then a social component. So it's kind of a nice example of IGert really kind of paying off in that respect. So anyway, congrats again.
Cool. Thanks for coming. Eat up if you have any more food. All right, let's stop the live
Is that Mark
broadcast.
still out there?
He is.